Hello class. So for this video, we're going to start on this new topic that I mentioned in the previous videos called classification of ODEs. If you're following in the book, which again I recommend that you are, this is chapter 1, section 3 in the book. Now before I start on this section, let me leave you a practice problem for you to work on. So in the previous videos, we saw how to find the general solution for certain families of ODEs. So as an example, or as a practice problem, why don't you try finding the general solution? So as you find the general solution, and again, this is the same as solve for the ODE given by, and we're going to recognize it, m dv dt equals negative mg plus kv. And now I'm just going to give you some things where m is not equal to 0. And then I guess that's, so g, you know what it is. You can just leave it as g. But what's important is that g, m, and k are all constants. Yeah, so try finding the solution for this differential equation, the general solution. You can see that, as I mentioned in previous videos, it's in the right form, right? If you rearrange it a little bit, just divide by m on both sides, you get something that looks like a derivative equals a constant plus a constant times the function. Right, so you should be able to do this. Okay. So going back to classification. So I mentioned that we already talked about one form of classification, basically type. There's either ordinary differential equations or partial differential equations. Now, the second way to classify things is order, and then the third way is linearity. So these are the three ways or main ways I would classify differential equations. Now, the order is actually a very easy one, so I'm not even going to write it as a definition. So what's the order of a differential equation? It's the order of the highest derivative that appears in the equation. As simple as that. Look at the equation, look at the highest order derivative. Okay, that's the order of the differential equation. So let's see examples. So let's find the order of the following differential equations. So let's look at negative 8 times second derivative of y plus e to the xy equals 2. So I already have the answer written down, but let's see why. Okay, so just look at this equation. It's a differential equation because it has derivatives. And you see that the highest order derivative you see is order 2. So you're taking 2 derivatives there. So the order of this differential equation is 2. Let's look at the second one. It's a little bit trickier. You have the fourth derivative of y with respect to x plus dy dx to the 7th equals cosine x. Again, this is a differential equation. It's an equation involving derivatives. Now, what's the order? I claim that the order is 4. Now why is it 4 and not 7? So we can clearly see that there's a fourth order derivative. Right here we're taking the derivative 4 times. So at least it's 4. Now, the only thing you have to be careful with is it's not 7 because dy dx to the 7th is not taking the derivative 7 times. It's multiplying the function dy dx by itself 7 times. Okay? So in other words, dy dx to the 7th is not equal to, so it's not equal to the 7th derivative of y with respect to x. It's not equal to this. It is equal to dy dx times dy dx times 7 times. Right, so there's 7 of them here. So it's basically the only thing you have to be careful. You'll see powers of derivatives like this, not higher order derivatives. So when I say order, I'm talking about how many derivatives you're taking. So you might see both higher order derivatives, like in this case, and also products of derivatives with themselves, right? So powers of derivatives. They're not the same thing. What matters is the order, not how many times you multiply a derivative by itself. Okay. So again, just simple process. Look at the equation, look at the highest derivative you see. Okay, in this case, for example, it's the fourth derivative of y. That's the order. Okay, so very simple definition. Now, since I mentioned that we're going to be talking about powers of functions as well as derivatives and higher order derivatives, then I need to introduce some notation. So basically, when I write something like this, this means the nth derivative. Oh, not squared, nth derivative. This means nth derivative. If I write y to the n, this means y multiplied by itself, n times. So I introduced this so I don't have to keep writing, if the independent variable is clear, I might just write this instead of writing this because it's less writing, right? So as long as the independent variable is clear, I'm probably just going to use this here. So the way to remember this is in an exponent, parentheses means derivative. Like this, just a function to a parentheses power, that means derivative. Now linearity. This is the last type, right? We had, so not the last type, the last form of classification. So again, we had 3. We already went through type. We went through order. Now we have to do linearity. It's hard because you kind of can only define linearity in a general way. Thankfully, in this class, we'll rarely work with differential equations that are order 3 or greater, right? So we're usually just going to work with differential equations of order 2 or less. So the highest derivative you're going to see is a second derivative. But still, I'm going to introduce linearity in the most general form. Okay. So definition 4. An nth order differential equation is linear if it has this form. You can write it as some function of x times the nth derivative plus some function of x times the nth minus 1 derivative. Right? And actually, let me underwrite it. I underwrite them as I go. So a and the a's are just functions of x. That's why they have parentheses x. Right? So you have a function of x times the nth derivative, a function of x times the n minus 1 derivative, all the way down until you get to a function of x times the first derivative, plus a function of x times y equals some function of x. And then in this second line, it's just the same thing, but I used the notation I introduced before. So instead of writing d superscript n y divided by dx to the n, I just write this notation y to the nth power in parentheses. And again, I don't have to write parentheses x after the y because you can see that the independent variable here, you can also see it here. So it should be clear that the independent variable is x. Okay. But this is basically the idea. Again, it's a little bit hard to see when the equation is written in such general terms. I'll of course give examples in a moment. But again, the important thing is that you have higher order derivatives. The only constants that you can have, or the only coefficients of higher order derivatives, can be functions of x. That's basically it. If you have a bunch of sum of derivatives whose coefficients are functions of x, then you're good. Now, of course, these functions can be anything. They could be 1, so there's no coefficient in front of the derivative. That's fine. Okay. But take a look at this, look at how this form looks, and try to, come to grips with it. The easiest way, however, is to just look through an example. So determine whether the following differential equations are linear. So start with number 1. So this one is linear. Why? Because it's in the right form. You have a derivative. Doesn't matter the order. You have a derivative. The coefficient is a function of the independent variable, which in this case is t. Right? 1 is a constant function. Plus, okay, there's another derivative. You have to make sure that the coefficient in front is a function of t. Oh, it's a constant again. Okay, constants are functions of t, so that works. Plus 5 times y again. This is a derivative. This is basically y to the 0, right? So y as a function, you can think of it as being the 0th derivative. Okay, so if you see another derivative, the 0 one, okay, whatever's in front has to be a function of t. Okay, 5 is a function of t. It's a constant function, so that works. And then whatever's on the other side that has no terms of y should be a function of t. Okay, cosine of 3t is a function of t. So this works. This is linear. Let's go with the second one. We have, so we have one derivative here. We have second order derivative. Again, doesn't matter the order of the derivative, that's fine. Okay. Now the coefficient should be a function of x. Okay, t, sorry, the independent variable. Okay, t squared is a function of t. We're good. Minus 4 times the first derivative of y. Okay, there's a derivative. The coefficient should be a function of t. 4 is a function of t. We're good. Equals negative sine t. Whatever doesn't have the variable y should be just a function of t. Negative sine t is just a function of t. Okay, so this is also linear. Okay, now number 3. So we have a second derivative. Okay, so the coefficient, actually let me do it in a different color. Let's use dark blue. So we have a second derivative. The coefficient should be a function of t. Okay, t squared is a function of t. We're good. Plus, okay, we have another derivative. So the coefficient, whatever's in front, should be a function of t. However, that's not the case. Okay. So it's true that y is a function of t, but since we don't know what y is, we don't know what expression it is in terms of t. So we can only leave it as a y. Okay. So technically, it is a function of t. If you want, you can, instead of saying it's the coefficient a function of t, you can say it's the coefficient an expression involving t. Right? So in this case, you can see that 4y is not an expression involving t. So as soon as you see this, okay, the coefficient of a derivative is not an expression involving t. Okay, so it's not linear. Okay, let's do another one. It's number 4. I'm actually going to use expression in terms of function of t, just to make it more precise. So we have a derivative, this is y dx squared. The coefficient should be an expression involving t. Okay, 1 is an expression involving t. It's a constant expression, so that works. Plus 3 dy dx. Okay, it's a derivative. Whatever's in front should be an expression involving t. Okay, it works. T is a constant. 3 is a constant, so it's an expression involving t. You can think of there being a t to the 0 in there. Okay. Minus 2 times y. Again, y is a derivative. You can think of it as a 0 derivative. So the coefficient should be an expression of t. It is. Right. 2 is a constant. It's an expression of t. Equals 0. Again, whatever's on the other side, or whatever doesn't have the y variable in it, should only be an expression of t. 0 is an expression involving only t. So again, it's a 0 expression. You can think of it that way, a constant expression. Another way that maybe would even be better to say it is you can say an expression involving no dependent variables. That would probably be the most precise way to say it. So I might actually, no, that's fine. I think the point is clear. If the expression involves y's, if the coefficient in front of the derivatives involves y's, then it's not linear. That's what you have to look for. This one is linear. Now let me do one more. Suppose we have, oops, y squared, say, the second derivative, not y squared, the second derivative of y with respect to t times t plus 3t equals, plus 3y, sorry. Oh, actually, this is good. Plus 3t equals 0. Is this differential equation linear? Okay, it is. There's a derivative here. So whatever's in front of it should be an expression only involving, not involving y's. Right. It is. It's an expression only involving t, so that's good. Now, there's no other derivatives. Right. That means that the only other thing you have to check is that anything that doesn't have a y in it should only be a function of t, or should only be an expression involving t, or should be an expression without involving any y's. In this case, 3t is an expression involving only t's and a constant, so it's not so it works. And 0, again, doesn't involve any y's. So again, it works. So this is linear. The other thing you have to be careful, let me write the same thing, but I'm going to write it, similar thing, I'm going to write it like this. Okay. If you look at on a differential equation like this, if you see something like this, a higher, not order, but power of a derivative, then it's immediately not linear. Right? So anytime you see a derivative times a derivative, it doesn't matter what orders they are, then yeah, then it's that works. Then it's not linear. Okay, immediately. And that's basically it. It is kind of hard to see at first, but again, the best algorithm to do this is look at your equation, find all derivatives, look at the coefficients of those derivatives. Do they involve only independent variables and constants? So whatever the coefficients are, if they're not involving the dependent variable, which in this case is y, then you're good. Remember, that's what we did. We looked at derivative, checked whether the coefficient is an expression without any y's, only involving t's, the independent variable, and constants. So go over all derivatives, check that that's the case, then go look for anything that doesn't have any y's, and that thing should also be an expression without any y's, only t's, the independent variable, or constants. And that's basically the idea. So these are a couple. Again, if you want more examples, this is another reason why I recommend the book. You can go through the book. Again, it's a section 1.3. You can look through the worked examples, and then at the end of each section, there's also practice problems. So you can also work through those, and they have solutions at the end of the book. Okay, so it's a good way to practice. But that basically sums up what we're working with in terms of classifications. We're going to be working with three forms of classifications: type, order, and linearity. And for the most part of this course, we're only going to be working with linear ODEs. Very rarely we're going to be working with non-linear ODEs. Right? So only ODEs that have this nice form. Okay. So that's it for this video. We'll continue, working on some things in the next couple of videos. But hopefully this was good in the sense that the examples were enough. Again, if you need more examples, feel free to go through the book. And if you have any questions, please just feel free to ask me.